Hello once again. Sorry about the trouble a little bit earlier. I'm Rhushik Matroja. I'm one of the co-founder and CEO of Cognitive Design Systems, based in south of France, Toulouse, to be specific, in the heart of the aerospace valley of Europe. We are a 3 years old startup, and we have big dreams, doing some crazy stuff. And let's show you some of those things. So first, I want to start with the bottleneck of additive manufacturing industries. So these are some charts that I found online from Materialize, saying that what is the main concern with additive manufacturing. Maybe many of you have seen it on LinkedIn. And we can clearly see that the design for additive manufacturing and data preparation are kind of as important as the machine cost. It looks like this. There was some other website showing that what are the 10 biggest challenges of additive manufacturing. And that's where we saw that, okay, of course there are concerns with the slow production rate from machine side, material development, manual post-processing. But then there is also a lot of things about design. We need to get the design right, get design ready for the additive manufacturing processes. We also need to educate the workforce, also engineers and technicians who are familiar with traditional manufacturing processes. We need to bring the education on additive side. Same with developing a business case. And it looks pretty obvious that from our perspective that additive is always a good case. But it's not. We can't do everything. It's not that cheap either. So we need to find the right business cases. So, and there are many other things. So we at CDS are focusing on 6 of those things. It's a big task. But we want to make sure that all these challenges are reflected well in our software suite, and that's what we are bringing to the market. And one thing is what are the biggest industrial challenges that I can summarize in 3 questions that maybe companies are asking themselves is how can additive manufacturing benefit my business? Identifying the opportunities. And what do we mean by opportunities? It's a cost saving, lead time saving, carbon footprint reduction, weight optimization, etc. Then there is also, once you have already a large department of innovation department on additive manufacturing in large organizations, then the question also, how can I store the know-how from the experts and redistribute it to the other people around the organization. That's also a challenge that we believe is true, and that's what we have seen it in automotive and aerospace industry that we work with. And the third one is how to think AM from the beginning while conceiving a product. And that's where we need innovative workflows where we can actually convert those opportunities into something more tangible and make something happen out of it. So in order to do that, we started by creating a software which does which answers to the question, where can AM benefit my business? By identifying the opportunity for cost, lead time, carbon footprint. That's once we have identified those opportunities, not all the parts that we can see in the industry are already ready to be manufactured in additive. It has to be sometimes adapted for this purpose. And I'm sure there will be some other talks later on. We will be talking about it. The second one is once I have that know-how on additive, how can I propagate? For that, we created a software called Cognitive Additive, where you can actually store your know-how and redistribute it to the others who are maybe not as familiar as you in additive manufacturing. So that's also a key point for us. And the last one is something that we are going to present for the first time today, is cognitive design. It's our computational design software, where we can rethink on how we are conceiving, but also adapt the interface to the expert label that is in front of the software. And in order to do that, we are creating an industrial know-how asset manager where we can able to collect all those insights and redistribute through these different softwares, so we can design better, we can produce better, and we can make something out of additive and find the right business cases. So it's pretty simple. We collect those data and we have this database, and then we redistribute it to the various designers, AM operators, technicians, so they can access to the understanding of how much feasible is my part, what is the cost related with my part, what is the carbon footprint related with the manufacturing process itself. That's our first step. On the screening side, of course, as I mentioned, cost saving, lead time saving, and CO2 savings are key. We are able to take into account all the large assemblies or the BOM of BOM of organizations to find those opportunities. Same way with the cognitive additive, you can do very quickly based on your database, based on your experts know-how, do the feasibility check, costing check, sustainability check. The costing model is based on how can I say, the industry standards, and that's where we leveraged it to it's not just printing. We have pre-processing, post-processing that we need to understand, because sometimes those costs can go up to 40 to 50%. Same with the sustainability. There is a lot of now new trend, and of course in Europe it's something more and more important. There will be some standards which will come out and on the European Union side, so we need to be prepared for it to bring something out of it. And the last is cognitive design, how to design better. So our approach, we are coming from the manufacturing industry. My background, my colleagues' background are also from manufacturing industry. We were producing parts, we were failing them, and we understood that, okay, where are the issues while designing the component. So we wanted to make sure that all the components which are coming out of my software has to be manufacturable. Because if it's not manufacturable, it's an art, and that's great, huh? But it's not always our purpose. Also in the large organization, industrial organization, that's not always the purpose. So we created this software where we automate DFM. So we will show you. We were able to create workflows using our geometry engine to automate the various different time-consuming processes and steps of modifying a geometry into a manufacturable geometry. Second is how to leverage the opportunities that AM is providing us, lightweighting, part consolidation, mass customization, also adding functionalities to the part is part of it. And at the end, we want to make sure that these large workflows sometimes are created by experts, the expert engineers or doctors, but it has to reach to the masses. It has to that anybody, as my friends at Trinkle mentioned, even the doctor in the dental studio, they should be able to design for their need, and that's what we are bringing at the end. So, manufacturing-driven design. We are trying to bridge the design and manufacturing by doing this. And for that purpose, we have two different categories of workflows. First is the product design cycle acceleration workflows, and the second one is the productized workflow for non-specialists for this purpose. The idea of the product design cycle acceleration is how to make sure that all designs are manufacturable. How can we automate the tedious and repetitive tasks to accelerate them, and take informed decisions while conceiving the product. The second one is how to adapt our UI to make sure that anybody from somebody on the shop floor to the somebody in medical how can I say the bureaus, medical design bureaus should be able to design without having to have a knowledge of computational design. So how can we package it in this way? So let's start with the design cycle acceleration. So this is a workflow that was kind of produced by all the experience we got in automotive and aerospace industry. Of course, I have linearized it, but it's not as linear as it looks like. We are able to, what we do is we do the ideation on the CAD software. Sometimes we do shape or topology optimization. We do the reconstruction of topology in CAD. We do the design for manufacturing, FEA validation. There are some iterations between these two happens all the time because we need to make sure that the products are also as can sustain the loads. And at the end, we do the fine tuning of the CAD to make sure that product is ready for the market. In our experience, we saw those workflows at various different companies, which takes up to 600 to 800 hours of engineering time. That's quite a lot. Most of the time is going on the design for manufacturing. That's where the biggest, because it's not the same department. So the information is sent to another department, bring back. There is a going forth and back. And that takes a lot of time. So we wanted to bring those insights into the CAD environment to do that. And in order to do that, we created our workflow where we automate some of those time-consuming processes. So with cognitive design, we are able to easily create those the ideation, so the rough CAD. We can also, once the topology optimization has done, do the reconstruction of topology optimization automatically. I will show you that. Manufacturing driven, same way. Convert the part into a manufacturable part this way. And at the end, the fine manual optimization also can be done. And we demonstrated with our customers that we were able to reduce the time by 90%. And these are the hard facts that we did in aerospace industry with Safran, with some other, in Japan side, it was Mitsubishi Electrics. On automotive side, Nissan and Yamaha. Why there are so many Japanese names here? Because I used to work there for 8 years, so that's why we continue working with them. But we also believe that these workflows can apply to more consumer goods, and that's what we demonstrated with Adidas and Oberalp. So cognitive design is a software which is engineered by engineers for their need. It's a hybrid modeling engine with a visual coding interface. As you can see, there are multiple viewports that you can look into it. You can compare. It's easy to compare with that. Its focus is on the automation of design. So we create this macro blocks or workflows which has focus to automate the tedious tasks of designs, of filleting, of Boolean operations for that purpose. And at the end, we also have this manufacturing analysis view where we can see that, okay, while conceiving the part, is it manufacturable? Where the issue is, where the wall is too thin, where there can be any issue with the support structures. So those are able to be done, so we can iterate it much easily in the same environment and faster. We focused on 6 different workflows. These are the primary workflows. We will be continuing developing new workflows afterwards. But first workflow is design for additive manufacturing. How can we automate that? Second is simulation-driven lightweighting or design in general. How can we modify the geometry to make it lightweight but still manufacturable? Topology optimization reconstruction. That is a personal choice. I was spending too much time doing that while doing topology optimization on various CAD tools that I can't name. But yeah, well, I wanted to automate it so we can actually spend some more time on creating different variations. Then design for molding. How can we adapt any kind of mold design, any kind of geometry into a moldable design? So we start with a two-part mold, simple one. We will go in detail further after how can we do much complex molds. We also do the mold generation itself, because once we have the workflow set up, we can just put a part and bring out the molds, and we can print with the cooling channels, which comes after, where you can select that, okay, based on your stress, the thermal stress, where the cooling channel should pass through, and it creates automatically. So the AM morpher, the idea is to not spend time on CAD while changing the geometry. Moreover, we are trying to reach complex geometries. Those complex geometries are not always easy to be modified in CAD, because we need to find those structures everywhere. So this is a very simple example, but imagine a heat exchanger with a lot of thin structures. And how can we modify those structures automatically, so we can make it manufacturable easily. Also add some ribs if the wall is too thin, and to bring some stiffness to it. Hole modifications, first of all, do the feature detection on the mesh of the holes, and once it's detected, convert them into diamond or teardrop shape. So we can print it easily, also add some over thickness easily. Same with the smart hollowing to do the thermal management. If you have data from the thermal stress data, how can we create the void, but also create the self-supporting structures internally? So we are able to print it easily without having to have internal supports. So that part is done with just one block here. You convert it into that design pretty easily. Something which we are working on, and it will be ready for the form next, is overhang optimization. Also modify the overhangs mathematically, so we don't have to work on it manually creating, because of the geometry is coming out of topology optimization. It's not always easy to work on it, so that's what we automate. Second one is the simulation-driven lightweighting. So this example is we used a lot in aerospace industry. They wanted to keep the part almost same, but they wanted to add some reduce some weight. So based on stress, we changed the thickness of the geometry, and we reduced the weight like that, and we were able to obtain with up to between 15 to 20%. It's not as large as topology optimization, but it's something which is a low-hanging fruit, I would say, that needs to be captured. Then the topology optimization post-process, it's pretty much all the Boolean operations, all the operations to reconnect the zones which are disconnected, needs to be also automated. There you go. Yeah. So what we did is that we bring in the design space, we extract the functional regions automatically, and we put the raw topology optimization part, which comes out of other softwares. And there is just one block which calls topology optimization post-process, and in few seconds you have your part ready, and that can go into manufacturing analysis process afterwards. Another one is the mold generator. Sorry, yeah, I think the video. Yeah. So the mold generator, we work with the mold manufacturers, but also with the injection molding companies to have a design of their mold that can fit in their machines for injections. So what we did is that we bring in the part, we select few zones where we want ventilation, where we want ejector pins, where we want injection, and based on that we create a mold. You can see it's I think it's accelerated 2 times, but not that much. You have this two part of mold which is ready to bring it out. All this is great, but we currently, all the mesh that we are bringing out are mesh models. And we are working, and I will talk about it later, on R&D, how to convert it into a step model with the feature detection. So a little bit different than what we have before, currently in the market. Then the second workflows are productized workflow, where we supercharge operators with computational design, so they don't have to be specialists of computational design to use it, to leverage it. What we did is we automate the creation of simplified UI directly from our computational design engine, so we can create that. Okay, there is input, output, and a 3D model in between. And so you can create workflows, you can share with your colleagues, and easily use them for that purpose. Something which is not automated is the add-ons and plugins that we work with our partners, such as Cinera, GrabCAD from Stratasys, but also Autodesk. Some specific workflows that we automated are paper pulp mold, CMM fixtures, texturing from an image, dental aligners, surgical guides for dental. And all this don't need the computational design thing. You just import your 3D model. It's a import 3D model, export 3D model kind of workflow with a few parameters that you can tweak. So you are able to easily generate your models. And we let the experts do the computational design so they can create the complex workflows, provide the right inputs and outputs. So there is no, how can I say, so there is a flexibility there. We also work on the orthopedic insoles with the same purpose. We brought this workflows and add-ons on as I mentioned, on GrabCAD, Cinera, and Fusion 360. On Stratasys, the focus was that okay, the machines are used on a shop floor. They are not used in a design bureau. These machines for mass production are operated by technicians and operators. They should be able to design themselves for their need. It can be jigs, fixtures, but also in the dental industry, dental aligners, surgical guides. They are not CAD operators there. So that's what we are doing it here with GrabCAD, and we automate this pretty easily inside the GrabCAD environment, so they don't have to go out of it. With Cinera, similar kind of workflows, but more complex designs. So simulation-driven design workflows, design for molding, topology reconstruction workflows, and cognitive adequate workflows are already present in Cinera, and you can leverage it with other Cinera tools or Cinera's partners tools, so you can create something much more valuable, much larger engineering workflows with that purpose. And in Fusion 360, it's pretty simple. We started with the jigs generator. You put your part. You have few parameters that you can tweak what is the large of your jig. It's a CMM jig, and then you click OK, yes, and it's a real time, so you have the part ready. And this is something which is very simple, but it can be used by operators very easily. And the last point is what we are doing in research and development. So all this workflows, and they are exporting mesh. And we all know how much industry loves the mesh, STL, right, Duan? So what we are trying to do is, of course, there is an alternative at 3MF. That I have to mention, but we also want to bring it to the in a BREP format. So we did some really great research on it together with an engineering school in France. We were able to convert 2D drawings into a BREP models. Of course, automatically. We use various different machine learning algorithms to do that, and results are very promising, and by the end of the year or beginning of next year, we should be able to bring it to the market. And then if you want to partner with us, we're very happy. Also with the mesh, we have all the mesh coming out of our geometries, but we need to make sure that it has to bring back to the CAD. So of course there is this motorcycle graph kind of mesh generation with the patches, but we all know how difficult it is to use. So what we are trying to do is we want to detect first the feature detection. We detect the features on the mesh itself, and then we convert it into the BREP features, and we create this model. We have some really great results at the moment, and we'll be integrating into our solutions going forward. So that's us. We connect design engineering with factory floor, basically in both ways. And by bringing the insights of manufacturing to the designers and bringing the design tools to the factory floor. And if you want to have manufacturable designs, contact us. There are some free softwares available on our website. So also the cognitive design, we can provide it for you for free for a short period of time, of course. And happy to collaborate on that. Thank you very much.